here this question is asking the power spectral density of a random process x of t is shown in figure P5.15. Determine and sketch the autocorrelation function Rx of tau of x of t. And B part is asking what is the DC power contained in x of t, and what is the AC. C part is asking what is the AC power contained in x of t, and D part is asking what is the sampling rate. Will give it uncorrelated sample of x of t, and are the samples statistically independent. Okay, so here we have a diagram provided, and this is in the frequency domain. We have frequency starting from negative f0 to f0, and also we have an impulse function right here that's at the origin, that is delta f, that's also frequency domain. So in order to find the answer in time domain, we have to do the inverse Fourier transform. So here the first part is determine and sketch the autocorrelation function Rx of tau of x of t. To find that one out, what we have to do is we have to, it's a combination of two of these, like it has this impulse function and also this triangular function. So we have to find out the inverse Fourier transform of both of them, and we have to add them together in order to sketch this diagram. Okay, so let's mention that we are doing the A part. Okay, something wrong here. Okay, let's do it here. So A part, the power spectral density consists of two components. The power spectral density consists of two components. One is a delta function, at the origin, delta of t, actually delta of f here is in the frequency domain, at the origin, whose inverse Fourier transform is 1. Okay, and then we have also a triangular function here, so let's mention that one as well. A triangular component of unit, a triangular component of unit amplitude and width 2f0, centered at the origin. The inverse Fourier transform of this component, the inverse Fourier transform of this component is f0 sin square f0 tau. If you wonder how did we derive this one, it's basically a triangular function. Like there's a property for Fourier transform That is, if you have a t over omega, that can be transferred in the Fourier transform in the frequency domain, that becomes an omega sin square t omega. Okay, this is for the triangular function, and whatever the value dividing here is the bandwidth. So in this case, if you look at the bandwidth here, that is f0. So we replace this one with delta t over f0 right here. So all the omega component will be replaced with f0. So f0 sin square t f0, and here the time is mentioned in tau, so we put the tau for it. Okay, that's how we derive this one. Okay, and that's part 2. Now we have to just draw this one. So here we are going to have a sin square function and also a 1 from the delta of, if you do the inverse Fourier transform of an inverse function, that's going to be just 1. So 1 and this, let's write the expression as well. So Rx of tau we can also mention, therefore the autocorrelation function of x of t is Rx of tau is equal to 1 plus f0 sin square f0 tau. Okay, and let's sketch that one. Okay, so because of this one, it's going to be shifted 1 unit to the upper side. Okay, and sinc function and sin square function, only one difference. Sinc function has a shape like this, but it will be going up and down of whatever the origin. Here our origin like it's shifted 1 unit up, so it will be going up and down for the sinc function. But sin square is only positive part of it. Like if it's in 0, it's going to be only having the upper part of it. And since we shifted 1 unit up, so it's going to have only upper part of it at this location. Okay, and here to determine what value should be here, you have to see what is below the tau. Here in this case we don't have anything below the tau, but if you put 1 over f0, that flips and comes to the top, so that is basically 1 over f0 in the below, so that becomes a f0 here. So this interval is negative 1 over f0, and this one is 1 over f0, and therefore each of them is just going to increase by 1, 2 over f0, and this is going to be minus 3 over f0, and so on. So 2 over f0, 3 over f0. Okay, and this is it for the A part of this question. They ask us to sketch the diagram. We had to first find out, like here we did the inverse Fourier transform of both of them. Inverse Fourier transform of this impulse function, that's just 1, and inverse Fourier transform of the triangular function is going to become a sin square function, and based on the bandwidth it's going to have the expression. So if you have a bandwidth f0, then it's going to be f0 sin square f0 tau. Okay, and we are drawing this one in the tau, that's time domain, and this graph is Rx of tau. Okay, and then B part is what is the DC power contained in x of t. So DC component is basically whatever that is not related to tau. So here if you look at the equation, you can right away find the 1 is the one that is not connected with the tau, so you can right away see that 1 is going to be the DC power. Since Rx of tau contains a constant component of amplitude 1, it follows the DC power contained in x of t is 1. And the C part is asking what is the power contained in what is the AC power contained in x of t. So in order to see that, you have to plug a 0 for this, the equation we found out here. So here we have f naught sin square f naught tau let's say you are taking Rx of 0. Sin is basically a function sine whatever the value over the same value. So if you put if you take R of 0, then sine 0 over 0. Okay, so that part will be gone. Then the part that will be left after Rx of 0 is just 1 plus f naught. Okay, let's write in a different way. We can also mention ex square of t is equal to Rx of naught 0. That will have 1 plus f naught, and 1 is the DC component, whatever left is the AC component. So here f naught is the AC component. The AC power contained in xf is therefore equal to f naught. Okay, now let's look at the D part of this question. The D part is asking what sampling rate will give uncorrelated samples of x of t. Are the samples statistically independent? Okay, so here from the graph you can see the tau has interval. It is having 1 over f naught, 2 over f naught, 3 over f naught, and then it's going on n over f naught. So it means the Rx of tau is equal to 1 doesn't depend on tau. It doesn't matter what tau has, but Rx of tau is going to be just 1 anyway. So that is uncorrelated, and Rx of tau is equal to 1 for n, tau is equal to n over f naught. Okay, and the sampling rate for correlation sampling rate for R uncorrelation is given by f is equal to 1 over tau, which is f naught over n. Okay, so based on that we can write the explanation of this. If the sampling rate is f naught over n, where n is an integer, the samples are uncorrelated. They are not, however, statistically independent. They are not, however, statistically independent. They would be statistically independent if x of t were a Gaussian process. They would be statistically independent if x of t were a Gaussian process. Okay, and that's it for this video. I hope you guys found it helpful. Thanks for watching. Don't forget to subscribe my channel. See you guys on my